This is Mr. G, and I'm going to talk about free fall. Free fall. That happens when you toss something in the air and you ignore all forces that might be acting on it except gravity. So, all objects in free fall, there's only one force, and I know we haven't really talked about what forces are exactly, and we will, don't worry. But for all objects in free fall, there's just the force of gravity, right? So that means that anything powered in the air that's not free fall, like airplanes, blimps, helicopters, drones, free fall, okay? And so we're going to look at two basic types of problem involving free fall, okay? Free fall, by the way, was studied in depth by Galileo, all right? Galilei. He came up with the law of falling bodies, in fact, which we've talked about. So for free fall, there are two types of basic problems at this point we're going to look at. That is when you drop something from a height above the ground. Okay, so let's look at that right now. And so it is the same four basic equations of motion that we're going to be using over and over and over again. We might change the symbols for certain quantities. So originally, we had, for example, delta x, that's change in position, is v naught times t plus 1/2 a/t squared. All right. But for vertical motion, that's motion that's up and down, there needs to be a way to distinguish this from motion that's horizontal. And so instead of a delta x, we're going to just say the distance some object falls is delta y, or that's its position above the ground. And again, you need a coordinate system for all these problems that you're working out. And so that is equal to, basically, its initial velocity times time, plus 1/2. And the thing about all objects in free fall is that they have the same acceleration, period. End of story. And that acceleration, if I draw something in the air here, let's say you just release something from rest. Right? And then here's something else that we have thrown across the room. There it is right there. And then here's something else that we toss straight up in the air. All three of these have the same acceleration. It's confusing, and it's not intuitive. It will be once we do a few more problems and talk about motion in 2 dimensions especially. So all objects in free fall have the same acceleration. Acceleration that has a magnitude and a direction. The magnitude specifically is, let's see. I'm going to put a little arrow here and label it with an acceleration, A. Same one with this guy, A. Same one with this guy, A. All three of these are accelerating downward at the same rate. The acceleration an object in free fall has is about 9.8 meters per second near the surface of the Earth, squared. But we're just going to say, we're going to call that value little g. Right? And to further simplify things, we're going to say that the value of little g that we use for our calculations, let's just make it 10 meters per second squared. All right. So all objects in free fall have the same acceleration. It is 10 meters per second squared down. That way. Objects don't have to be moving down to have a downward acceleration. They just have to be in a gravity field. Right? So that means that this equation here, the delta y, is plus 1/2 g/t squared. It's exactly the same equation as the one written above it. The same one we've been using to analyze motion of cars and rabbits and ducks. Only now we're using it to analyze objects that are in free fall. Right? Next, coordinate systems. Yeah, coordinate systems. So as you can see, even when I'm just drawing here, I try to put a background coordinate system on the page. That just helps me write. So you need coordinates. And right now, we're dealing with motion in one dimension. One dimension. That's either left, right, or up and down. Later, we'll be doing left, right, and up and down at the same time. That'll be fun. So a coordinate system. It's a ruler, all right? That shows you position. It could also show you velocities. And so let's go back to where we drop something. Right? We're actually going to have to go outside and drop some stuff, some more stuff. A TV set would be good. TV sets. No, I'm kidding. Don't drop a TV set, all right? So a coordinate system, it's a ruler, right, where we measure positions. So in any problem, the coordinate system can be arbitrary. You can make the coordinate system however you like. For example, this guy is going to use a coordinate system where the origin is right here. Right? So in other words, if we think of this as like an XY coordinate system, the initial coordinate of that TV set is 0, 0. Okay? And we can completely ignore the X coordinate because we're dealing with only motion right now that's up and down. Furthermore, the direction that you define to be positive is also up to you. You can make down positive, in which case I'm going to put a little arrow here with a plus to remind me that down is positive. So if I'm looking at distances, then the distances would be, let's say this is 5 meters, 10 meters, 15 meters, right? While going the other way, this distance would be, guess what, minus 5 meters. Up here at minus 10 meters, so on and so forth. Okay, so positions above 0 in this coordinate system are considered negative. Positions toward the ground greater than 0, those are positive values. Okay, so then the equation that describes how this is going to move, its position, delta y, is equal to v naught times t plus 1/2 gt squared. Now, remember that all objects accelerate downward in free fall. In this problem, with the coordinate system, downward is positive. That means that this guy is plus 10 meters per second squared. And so this really turns into, if you want to plug in the numbers, you could, at this point you could half times 5. And then you might be saying, well, then why don't you just write 5 instead of 1/2 g? Because we're going to use that g in other equations as well. And if I just write down the 5, you might forget that that represents, or it's proportional to the acceleration due to gravity. Okay? For objects in free fall, in fact, the acceleration is always going to be, how am I trying to say here? Whatever this number is, whatever that coefficient is, the acceleration is always twice that value. Right? And again, the best way to really understand this is to just work some problems. So let's work a problem. So what we're going to do is we're going to release something from rest. And a lot of you figured out already, released from rest, that means that its initial velocity is 0. That means that this v naught is 0. And 0 times anything is still 0. So this entire first term goes away. Okay. That makes the expression even easier to use. All right? So then that equation just basically turns into delta y is equal to 5 times t squared. All right? And that's it. This gives you the position as a function of time. Time is going to be measured in seconds here, right? And y is in meters. So let's figure out 20 meters. That's how high above the ground you are, right? So if I release something from 20 meters above the ground, how long will it take to hit the ground? How long will it take? How long does it take? How long does it take to hit the ground? Because some of these expressions, what it is we're trying to find, can sometimes be confusing. How long does it take to hit the ground is different from how far does it travel or how fast is it moving. So how long does it take? That's always going to be time. So you're looking for time, right? So algebra time. Speaking of time, yeah, let's just use a little bit of algebra here. Some easy peasy lemon squeezy algebra. Basically, the word is this. The expression is we want to solve for t. That's algebra for saying I want to know the value of t if I know everything, all the other variables in the equation. And there's only one other variable, and that's y, right? Delta y. And so again, you know, we should have done this in the beginning, but list everything we know. So we know that if we drop it from 20 meters above the ground, then delta y is 20 meters. We also know the acceleration is about 10 meters per second squared, g. And we release it from rest, so we know that v naught is 0 meters per second. So we just leave it out of the final equation. So now, solving for t. Let's see, how do we do that? You apply the rules of the rules of order when you're undoing an equation. So the first thing you do is divide both sides by 5. So that 5, that turns into 1, right? And so I have delta y divided by 5 is equal to t squared. And then to get the t by itself, I take the square root of both sides. Okay? And so on the left, I can finally plug in my numbers now. So I have the square root of 20 meters divided by, and the units on that 5, they're units of acceleration. So it's 5 meters per second squared. And that is equal to t. Okay. 20 divided by 5 is 4. The numbers here, 20 over 5 is 4. Furthermore, meters over meters, those cancel out. Boink, boink. And then 1 over seconds squared, believe it or not, is seconds squared. All right. So the square root of 4, that part is 2. And the square root of seconds squared is seconds. And that's consistent. We are looking for time. And now we have it. 2 seconds. It takes 2 seconds to strike the ground. And if you're saying this problem was really easy to do, right? Are they all going to be like this? If you practice them, they will all end up being this easy. But don't be fooled. These are really not that easy to work out. You really don't know how well you understand this until you start to work out problems on your own, without looking at your notes, without any help at all. All right? It takes practice. Trust me, it takes a lot of practice. So let's practice another one. Here we are again. I really hope that you're getting as sick of this stupid building as well, I'm not really sick of it. Okay, so here we go. Yes, another building. That reminds me of something. More songs about buildings. Buildings and food. Google it. More songs about buildings and food. Buildings and food, yeah. Okay. So here we have a building. Let's say we don't know how high it is, right? But this time we're going to drop something from rest, right? So V naught is 0 meters per second. But you have a little timer here, tick, 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 and you're measuring time. And so we're going to release it from rest, and it is going to fall, sploop, and hit the ground, all right? And that is going to take 4 seconds to hit the ground. And we want to know how high is the building? So what is delta Y? And let's also figure out how fast is it moving just before it strikes the ground. So that's V final. All right, so first, establish a coordinate system. The one we used for the previous problem works perfectly well for this problem as well. So my coordinate system is basically like this, and down is the positive direction. All right. So I want to know delta y. Well, we have an equation for that. Okay. Delta y is equal to V naught times t plus 1/2 gt squared. You've released it from rest, so once again, that V naught is equal to 0, and 0 times t is 0. Right? So then, again, this turns into delta y is equal to odd half of 10 is 5 times t squared. So we can solve this directly by putting in the value of t. So delta y is 5 times 4 seconds squared. And the units on this 5 are meters per second squared. All right, 4 squared is 16 seconds squared. So 5 times 16 is 80. All right, and so you've got this seconds right here is squared. That cancels with this seconds squared, and you're left with meters, which is good. So it fell 80 meters. When you drop something from rest and it takes about 4 seconds to hit the ground, the distance it falls is about 80 meters. Next, what is its final velocity? Let's think about this. And again, there are different ways of answering these questions. Sometimes if you look at the information, if you understand what acceleration is, you can get the answer without even writing anything down. All right, so I'm looking for V final. Well, here's the deal. I know that when I release it, it is accelerating downward at about 10 meters per second per second. That means every second it's falling, its velocity increases by 10 meters per second. So starting from 0, how much is it going to be after 4 seconds? Yes, it's going to be 40 meters per second. If you want the equation, we have that. That one is V final is equal to V naught plus A times T. V naught is 0. The acceleration is 10 meters per second squared. The time is 4 seconds. So the number part, 10 times 4 is 40. The unit part is seconds divided by seconds squared. And then you got a meters up here also. So that leaves you with meters per second, which is the unit we want for velocity. Okay, I'm going to stop and upload this now.